Hi friends, welcome back. Today we are discussing about how we can answer the question in biopharmaceutics subject. I think based on my students' opinion, the subject may be complicated because the main thing what we can do in the subject is that make the ideas clear. Then we can easily score in this subject. So today we are going to deal how we can easily score or how we can answer the questions in biopharmaceutics and pharmacokinetics subject in 6th semester B Pharm as well as Pharm D. So let's start the Today we are focusing on the kinetic topic, mainly on the short answers we can expect in the kinetic part. We are only discussing about the most important topic coming under kinetics. So the first question is about maximum safe concentration and minimum effective concentration. So here we have to draw a graph that is versus plasma concentration versus time. So we can see a curve like this. We can see the onset of action, onset time, then first we can see the absorption phase, after that the absorption rate become equal to elimination rate, and after that post absorption, and finally elimination phase. So we can see two terms, that is the MSC, that is the minimum safe concentration, maximum safe concentration, minimum effective concentration. We can see the duration of action, AUC, like that. So our question is about the dynamic parameter, that is a minimum effective concentration and maximum safe concentration. Minimum effective concentration means the minimum concentration of the drug which is required to produce a particular therapeutic effect. If it is below that, we are telling it as subtherapeutic level, but in case of antibiotic we have deal with another term, that is minimum inhibitory concentration. So here we are dealing at minimum effective concentration. Then next about the maximum safe concentration, that means the concentration in plasma above which it may lead to adverse or unwanted effects, or we can see a precipitation of the unwanted effect. So the concentration above this maximum safe concentration may lead to toxic level. Next question is about loading and maintenance dose. So we can see that an initial or what they are giving as a first dose to form therapeutic effect is known as priming dose or loading dose, and we are representing by capital D subscript 0, L. So we can correlate this in steady state concentration. Whereas maintenance dose means we are giving this dose to maintain a concentration at the infinite time and at steady state so that we can maintain the therapeutic effect. And the ratio of loading to maintenance dose is known as dose ratio. We already mentioned loading dose is D subscript 0L, whereas maintenance dose is X0. So the dosage interval is equal to half-life. In that case, we can see the dose ratio should be equal to 2. Whereas when the interval is greater than the t half, then the dose ratio should be smaller than 2. And if the interval is less than the t half or half-life, it may result in a dose ratio should be greater than the 2. So this is the graph we have supposed to draw, that is a plasma drug concentration versus dosing interval. Here this is the loading dose, what we are maintaining is the maintenance dose. This is the dose ratio what we have discussed just now. The next question is about write about the flip flow phenomena and the lab time. So we can see that we are trying in kinetics to estimate either Ka or Ke, that is absorption rate constant as well as elimination rate constant, and we are determining or estimating the rate constant for the absorption and elimination by the method of residual. In that case, we are assuming that the absorption rate constant is very much greater than the elimination rate constant. But in some cases what happen is that the elimination rate constant become very greater than absorption rate constant, and we can find out the value of absorption rate constant from the terminal phase and elimination rate constant from the residual phase. So this interchange phenomena is known as flip-flop phenomena. So we can express by the equation. In flip-flop kinetics, the slope is equal to Ke divided by Ka greater than or equal to 3. But in normal kinetics, the vice versa, that is Ka by Ke greater than equal to 3. The next term is lag time. So we can see this concept if we are administering a drug orally of a single dose of a drug. So we can see a bi-exponential curve like this, and we can see the lag time here. So lag time actually means there's a time difference between the drug administration and start of absorption. Normally we are representing this lag time with the help of T0, and it represents the beginning of the absorption process. Next time, the mean residence time. So we can see this concept in terms of non-compartmental approach. That is, based on the statistical moment theory, we are applying the non-compartmental approach, and it involves the collection of the experimental data following a single dose of the drug. So we can see the mean residence time. So when we plot concentration versus time, this is the AUC and this is the AUMC. So we know how we can determine an AUMC. So mean residence time mean it is the ratio of AUMC divided by AUC will provide you as the MRT, that is the mean residence time, where AUMC is the area under first moment curve and AUC is the area under zero moment curve. So we can define this MRT as the average amount of the time spent by the drug in the body before being eliminated. Next question is about what are the limitations of urine data for calculation of pharmacokinetics. So we are using this urine data as a rough estimate of the pharmacokinetic parameter. What happens is that if a drug provides very slow release, or if the drug is having low urinary drug concentration, maybe too dilute, so we cannot tell it the result is accurate. Or if the drug is with long half-life also, the urine we have to collect for several days to account for total excretion. So these are the major limitations we can see with the urine data collection, and we are using two methods for determination of elimination rate constant from urinary excretion data. First one is rate of excretion method and one is sigma minus method. Next question, define catenary model and write its one application. So, for the analysis of pharmacokinetic data, we are depending either model or model independent approach. So, under the model approach, under compartment model, we are studying our catenary model. So, in the catenary model, this is a way of representing the catenary model. So, we can see three compartments. This is with the help of three compartments. We are explaining this is a central compartment and 2 and 3 are the peripheral compartment. So, this catenary model can be used in predicting the drug concentration time profile, and we can use in development of the dosage regimen as well as in relating plasma drug level and for drug comparisons. Next one, what are the limitations of one compartment model? Normally, we are explaining with the help of one compartment model, but the main thing is that we can apply only to the drugs which follow one compartment characteristic. And when we plot the concentration versus time after oral administration, some case we can see the multi-compartment characteristic, and on IV administration also the same problem. So in that condition, it may result in incorrect result. So these are the limitations of the one compartment model. So going to the next question, the name two parameter used in adjusting dosage regimen. So one is the dose size and second is the dosing frequency. This is a curve showing the dose size and plasma concentration profile. So you can see the curve like this. So if the dose is smaller, the drug will produce a effect less than the minimum effective concentration. So in between the minimum effective concentration and maximum safe concentration, here we can see an optimum dose profile, and if it is high, here the dose what happened, we can see the maximum fluctuations in the therapeutic and toxic response. And the next parameter is dosing frequency. Frequency means the time interval between the dose. So explain with the help of the schematic representation. So we can see if the frequency is less, we can see large fluctuations and it may result in therapeutic unsuccessful reaction. Whereas if it is optimal, we can see the interval become equal to half-life and result in therapeutic successful level. And if the dosing frequency is high, we can see lesser fluctuation, but we can see therapeutic as well as toxic responses. The next question, what are the significance of Km and Vmax? This is coming under a non-linear pharmacokinetics. So we have to draw the graph dc by dt versus concentration and have to represent the Km is equal to C. What is the condition? Km greater than C and Km less than C. So in the first case, we can see the difference, that is Vmax by T is the condition. So we can see that the rate of process here is equal to the half of its maximal rate. But when in case Km is very greater than C, what happened? We can see the first order elimination in such cases. So we can see this in usual dosage regimen. And some exceptional cases are the like phenytoin and alcohol. The third case is when Km very less than C. So we can see a kinetics, that is zero order process, and it is independent of the drug concentration. Mainly we can see in case of the metabolism of ethanol. So we have to draw the graph and explain the condition. So thereby we can find out the nonlinear pharmacokinetics. Next question, enlist factors causing nonlinearity. This is a very important question. That is mainly the drug absorption, distribution, metabolism, and elimination are the factors. Other than that, we can express the saturation of the enzyme, pathological alteration like that. So in the drug absorption, we can see the in case of solubility, carrier mediated transport, and hepatic metabolism. And the drug distribution case, we can see the non-linearity in case of saturation of binding site as well as saturation of binding site on plasma protein. Whereas in drug metabolism, we can see the capacity limited metabolism and enzyme induction. And in case of drug excretion, that is in the active tubular excretion and active tubular reabsorption. By this, we are coming to the end of this video. I hope this video will be helpful. Please share to your friends. Thank you for supporting. Thank you for watching.